Should I start?
Yeah.
He start.
So hello
Okay.
everyone. My name is Diaa, and today I'll be
Should
presenting.
present Hazem, first of all.
Yes, that is the thing. Let me present you as a. Okay.
Okay, I'm sorry.
Yeah, it's all right. I see you are very excited. So hello everyone. My name is Abba Ramadan. I am happy to be part of this program for the third year, and I would like to thank the organizers, Tuk Mathematics and also Sabanji and other sponsors for bringing this wonderful conference. And also want to thank the organizers, the past and the current one, for their wonderful work to bring this into reality. I also want to present Hazem, who is a third-year student in American University in Cairo, in Egypt. And today he will remind us a little bit about continuity and compactness. Hazem, you have the floor.
Thank you so much, Dr. Abba. I learned a lot from you during this program, and I thank you so much for this. And I'm sorry for rushing through the presentation. So hello, everyone. I'm Hazem Diaa, and today I'll be presenting one of the many great results of real analysis, which is continuity and compactness. Now, here is my outline. I will first give a brief overview of basic point set topological sets and the tools that we would need in this presentation. And then I will give the rigorous epsilon-delta definition of a functional limit. And we will move from this to see what a continuous function really is. And we will specifically discuss useful characterization of continuity, or a theorem that is an important result. And then we would move on to see how continuity kind of affects compactness of sets. And then finally, we will discuss uniform continuity. We will mainly give a quick comparison with continuity. And then again, we would end with seeing how uniform continuity affects compactness of sets. So let X be a metric space. All these points and sets are subsets and elements of X. So firstly, fix a positive epsilon. We say that an epsilon neighborhood of P is the set of all points Q and X whose distance from P is smaller than epsilon. A point P is a limit point of a set E if every epsilon neighborhood of P contains a point Q not equal to P that is an element of E. Moreover, a set E is closed if E contains all of its limit points. A set E is open if for all elements X in E, we can find an epsilon neighborhood of P in E. And I'm sorry, here it says X, but it should be P here. And finally, a set E is bounded if there exists a positive real number M and a point Q in X whose distance from P is smaller than M for every point P in E. Now let's have a quick intermezzo of giving a brief theorem, which is Hain-Borel theorem. It's known historically as that. So we let E be a subset of the Euclidean K-space. Then these three statements imply one another. E is compact, E is closed and bounded, and every infinite subset of E has a limit point in E. Now, for the sake of time, I won't cover the full proof here or the proof at all, because it's about 1 page long, but I would direct any interested one to Rudin's page 40. Now, let's discuss what is a functional limit. We all know from calculus what a limit is, but do we actually do? Here we would have let X and Y be metric spaces, E be a subset of X, and F be a mapping of E into Y, and P be a limit point of E. Then the limit of f of X as X approaches P equal to Q if there exists a point Q in Y satisfying the following property. For every epsilon, we can find a positive delta such that for all elements X and E, if the distance between X and P can be restricted between 0 and delta, then the distance between f of X and Q in Y is smaller than epsilon, where, of course, the dx and dy are the metrics or the distances in X and Y, respectively. Now, here is a geometric interpretation of a functional limit. So here is the usual xy plane or the Cartesian plane. And what we do here, we are given a positive epsilon, and we draw the lines L plus epsilon and L minus epsilon. Now, we say that the limit of f of x as x approaches x node equals to L, if and only if we can assert that for all, if we can assert that if we can restrict x to be in the open interval x node minus delta and x node plus delta, then we can guarantee 100% that the graph y equal to f of x would be between the two lines L plus epsilon and L minus epsilon. And here you can observe that for a given epsilon challenge, we can, of course, reduce the delta as well. So for any delta, any smaller delta would work as well. And now we move on to see what a continuous function is. Again, from calculus, we know that a function is continuous if we can draw its graph without lifting our pen. But in the realm of mathematics, that does not mean anything. Here, let x and y be metric spaces, E be a subset of x, F be a mapping of E into y, and P be a point in E. So if you are focused, you would see that this requirement was not a requirement in the previous definition of a limit. Then if is continuous at the point P, if the following property holds. For every epsilon, we can find a positive delta such that for all elements x in E, if the distance between x and p is smaller than delta, then the distance in y between f of x and f of p is smaller than epsilon. And we also say that if is continuous on the whole set E, if f is continuous at every point in E. Now, here is a useful theorem that we would want to deliver. A mapping f of x into y is continuous on x if and only if for every open set V and Y, the inverse image of V under F is open in X. So how do we prove such a thing? Firstly, the forward direction, we would fix a point P in X and F of P in V. Now, since V is open, then there exists a positive epsilon such that for all elements Y and Y, if the distance between F of P and Y is smaller than epsilon, then Y in V. And you can interpret this as if y is in the epsilon neighborhood of f of p, then y in v, or simply that the epsilon neighborhood of f of p is a subset of v. Now, by continuity of f at p, we can find a delta such that for all elements x small and x capital, if the distance between p and x is smaller than delta, then the distance between f of p and f of x is smaller than epsilon. But then notice that once this hypothesis is achieved, we will see that if we replace f of x here by y, then the following result follows, which is y as an element of v. But applying f inverse to both sides, we would see that x is an element in the inverse image of v. But then this is precisely what openness would be, because here we would have that the delta neighborhood of x is a subset of f inverse of v. Let's move on to the backward direction. So we suppose that the inverse image of V under F is open in X for every open set V and Y. Again, we fix a point P in X and a positive epsilon. And the trick is to define V to be the set of all elements in Y whose distance from F of P is smaller than epsilon. Or we can simply say that V is the epsilon neighborhood of F of P inside Y, of course. Then, of course, V is open, being a neighborhood. So the inverse image of V is open by hypothesis. Hence, we can find a positive delta such that for all elements x and x, if the distance between x and p is smaller than delta, then x is an element of f inverse of V. But then notice, applying f here, we would get that f of x is an element of V. So the distance between f of x and f of p is smaller than epsilon. This follows from the definition of V we gave. But this is actually precisely what continuity is, because once the distance between x and p is smaller than delta, we would guarantee that the distance between f of x and f of p is smaller than epsilon, thus establishing continuity. Now, let's see how compactness behaves under continuous mappings. So let f be a mapping of x into y be continuous on a compact x. Then the image of x under f must be compact. So the proof is to let the collection v sub alpha be an open cover of f of x. So f of x is of course subset of the possibly infinite union of v sub alpha. Now, since h v sub alpha is open and f is continuous, then theorem 2, which is here, would imply that each of the sets f inverse of v sub alpha is open. But observe that applying f inverse to both sides of the subset, we get that x is a subset of f inverse of the union of v sub alpha. And the equality here would follow from simply verifying that both sets are subsets of one another. Now, x is compact, so we guarantee finitely many indices from alpha 1 till alpha n, such that x is a subset of the finite union from f inverse of v sub alpha 1 till f inverse of v sub alpha n. Now, the image of f inverse of E under f is a subset of E for every set E and Y. But then equation 1, which is here, would necessitate that f of x is a subset of the union from v alpha 1 till v alpha n. This is again guaranteed by applying in equation 1 f to both sides of the equation, and thus establishing this theorem. Now let's visit another definition that would help us. A function f from E into the Euclidean k-space is bounded if there exists a positive real number m such that as the absolute value of f of x is smaller than or equal to m for every element x in E. And here is a corollary, an easy one that follows from the last theorem. We let f be a mapping of x into Rk, be continuous on a compact metric space x, then f of x is of course closed and bounded. And moreover, the function f is itself bounded. That is, the set of all values of f of x, or the range of f, is bounded. So this follows from, of course, the last two theorems. Now here's an important application of what we discussed, which is the extreme value theorem. And it's something we all covered in calculus. So let f be a continuous real function on a compact metric space x with alpha equal to the supremum of f of x and beta equal to the infimum of f of x. Then we guarantee that there are points p and q in x such that f of p equal to alpha and f of q equal to beta. Or in other words, we can say that the function f of x attains its minimum value as well as its maximum value for all elements x and x. And this proof follows from the preservation of compactness corollary we gave just recently, because f of x would be a closed and bounded set of real numbers, and alpha and beta, which are the supremum and infimum, are limit points of f of x. So since f of x is closed, then it equals its closure set. But then alpha and beta must be an element of f of x, thus establishing this theorem. Now let's move on to something that we actually did not cover in calculus, which is uniform continuity. So let x and y be metric spaces and f be a mapping of x into y. Then we call f uniformly continuous on x if for every epsilon we can find a positive delta such that for any possible pair p and q in x, if the distance between p and q is smaller than delta, then the distance between f of p and f of q is smaller than epsilon. Or we can visualize this proof as if we, for example, focus only on the element q here, that if q is in the delta neighborhood of p, then f of q would be in the epsilon neighborhood of f of p. So here is an important question that would arise. Which definition is stronger, continuity or uniform continuity? That is, which definition necessarily implies the other, but not necessarily the other way around? And here I remind you of the definition of continuity, so you can look at it once again. Of course, the answer to this question would be uniform continuity, because notice that in the uniform continuity we find a single epsilon that works for all pairs in X. That is, it works simultaneously for any challenge of points we are given in X, such that, of course, this property holds. But notice that in uniform continuity, we find a positive delta that is perhaps depending on P. We cannot verify, we cannot omit this possibility from the statement of the definition. Therefore, the answer is uniform continuity. And finally, let's give one of the main pillars actually of this presentation, which is how uniform continuity affects compactness. So let F, or I'm sorry, the other way around. Let F be a mapping of X into Y, be continuous on a compact metric space X. Then F is uniformly continuous on X. And here is one of the most elegant proofs that I have found in Rudin's textbook. We fix a positive epsilon, and we know that by continuity of F on X, we can assign to each point P in X a positive number phi of P. That is simply in the original definition would correspond to a positive delta, such that if X is in P and if the distance between P and Q is smaller than phi of P, then the distance in the images of these points would in the metric space Y would be smaller than epsilon over 2. Here, let us define the set G of P to be the set of all points in X whose distance from P is smaller than half phi of P. Trivially, we have P as an element of G of P, but then the collection of all sets G of P would form an open cover of X. So of course, X would be a subset of the possibly infinite union of G of P sub I. Remember, X is compact, so there are finitely many points from P1 till Pn in X, such that X is a subset of the finite union from G sub Pi to G sub Pn. Here, the trick is to set delta to be equal to half the minimum of all phi P sub I that we have just defined. That is actually the key to the proof. Of course, since delta is the minimum of a finite set of positive values, then delta is positive. Now, let P and Q let's define P and Q to be the set of all elements whose distance from one another is smaller than delta. By the second equation here, equation 2, we would see that we can find a positive integer that is inside the closed interval 1 to n, such that P is an element of G sub P sub m. But hence, the distance between P and P sub m is smaller than half phi P of m, because of course that follows from our definition of the set G of P. We also have, by the triangle inequality, that the distance between Q and PM is smaller than or equal to the distance between Q and P and the distance between P and PM. But remember, we said here that the distance between Q and P must be smaller than delta. That's just by our definition. And of course, again, by definition, the distance between P and PM is smaller than half phi PM. But since delta is the minimum of this set, then delta is smaller than half phi PM, and therefore 2 times half phi PM would be a phi PM. From equation 1 here, which is the statement of continuity, we would guarantee that again, the distance between PM and Q is smaller than phi P of M. That guarantees that the distance between f of P of M and f of Q is smaller than epsilon over 2. Therefore, it follows that the distance between f of P and f Q by the triangle inequality is smaller than this expression, the distance from f of P and f of PM and f of PM to f of Q, which each one of them is smaller than epsilon over 2. Therefore, this distance is smaller than epsilon, and therefore establishing the theorem. That's it for my presentation. I've used this seminal text, which I learned a lot from. And I would direct anyone interested in real analysis or analysis in general to reading this book. Thank you so much for your attention.
All right. Thank you, Hazem. And anybody with question, comment, remark?
Yeah, are there any questions, Hazem?
Are there any questions to me?
Yes, he's asking the audience if they have questions for you.
Yeah.
Maybe we forgot to stop the recording.
I'm sorry.